Okay, so last time we started talking about non-parametric regression, and the idea was that we have this generalization of linear regression, which you're all familiar with, where we observe a function evaluated at certain points plus noise, and this function is assumed, if a star is assumed to belong to some function class f. So in the linear regression case, this function class is just a set of all linear functions, let's say from Rd to R, in which case we can write any of these f as an inner product of some beta times x, where beta is another vector in Rd. So this is sort of an example of the Ries's representations theorem in infinite dimensional, let's say, case. Every linear functional on Rd can be represented by a single vector from Rd, in general from the dual space of Rd, which is, again, Rd. And so this f star would be like beta star inner product with x. And if you write down what these equations would look like in that case, it can be compact written as y equal x beta star plus epsilon, where x has these rows xi transpose. This is the classical linear regression. And then we discussed the general case a little bit, the possible estimators. So the estimator that we're going to focus on is this projection estimator. So we try to minimize, this is natural, so you try to find an f that minimizes this, but you're going to restrict to the class of functions that you're looking at. So if you do this for the regression, because this class is linear, this is effectively the ordinary least squares estimate. We can also regularize by some sort of a norm of f, let's say associated with class f. And in that case, the estimator, for example, the ridge regression would be an example of this. And in general, there's this idea of kernel ridge regression, which is an example of a kernel method. And we discussed this a little bit. I'm going to skip the details here, but if you're interested, we can go over this later. There's a whole chapter of the HDS book that talks about reproducing kernel Hilbert spaces and how non-parametric regression in those spaces looks like. The general idea was that you could write the function evaluations as basically inner products of certain functions in the RKHS with f itself. And so the problem reduced looks like as if you're dealing with a linear regression. It's not linear, but it behaves like linear regression. So these are representatives of evaluation, and they can be like exactly sort of determined as these kernel functions when you fix one of the coordinates. And so every RKHS has a kernel associated with it, and then these are the representatives of evaluation. So the problem very much looks like the finite dimensional case. It's not finite dimensional, but then you try to minimize something like that. And there's certain interesting examples of this, like smoothing spline, where this is a Sobolev space. This norm is like the integral of the derivative, L2 norm of the derivative, or derivative, second derivative, and so on. Okay, so that was the last time. So any questions or comments about this? I'm still on. You guys can hear me?
Yes, we can hear you.
Yeah. Yes, okay. So the last thing that I discussed last time was the performance measure, or performance measures. And as I mentioned, we're going to focus on the so-called empirical L2 norm. This is very common in statistics literature when dealing with non-parametric regression. And so the L2 norm is like taking the integral with respect to some generic x of this the squared deviation. The empirical L2, it takes the integral with respect to the empirical measure, and the empirical measure is just, if you recall from 200b, it's a measure that puts equal mass on every observed data point. So your training data set is, so training, let's see. Training is yi and xi. And so you look at this set of the observed xi's and you put mass 1 over n on every one. So this is like x1, this could be x2, this could be x4, this could be x3. I'm doing it in this could be x5 in 1 dimension. So you put like the point mass 1 over n at every point, and this would be the empirical measure. Size is like 1 over n. And so these are point masses at each point. So if you think of the L2 norm, L2 spaces associated with this probability measure, then there's a valid L2 space, and the L2 norm would be this, but the integral basically reduces to the sum. So you evaluate the functions at these points, and then you take the square of the function, and so in general, if I have f, then the notation is something like this, or L2 Pn. This would be 1 over n summation I from 1 to n f squared xi. So if you want to do like the L2 norm, that's the square root of this. Okay. So this is for very large n, if xi's, let's say, are uniform, or xi's are derived from basically p independently, then this is going to be close to the actual L2 norm. That's sort of by the law of large number, or by the uniform laws of large number and things like this. We're not going to worry about this approximation here, so we can just focus on this this norm itself. So anyone remembers, I mentioned briefly why, from a statistical perspective, this norm makes sense. Just curious, anyone got that point or remembers why we focus on the empirical L2? What is the statistical justification? Anyone? No one remembers? Okay, so the statistical justification is that this model is the f in this model is identifiable only at those points. So I can't really estimate anything about the or I can't really say once I have observed endpoints, I know anything about the values of the function outside. We're going to make assumptions, but there could be so that's not exactly true. But so if you make like a smoothness assumption, you know some sort of behavior in between. It can't be like arbitrary. But generally, there are many functions that satisfy your criteria and also pass through those points. And so from this perspective, this somewhat makes sense. Okay. Questions? Comments? Everyone good? So I'm going to skip the rest of these. We talked a little bit about that. I'm going to switch to the new slides. These are the same things that are in the previous slide. So what I'm now going to do is argue that this model can be reduced to this sort of normal means model. And this is a very interesting model, and many statistical problems can be reduced to this or variations of this, or non-parametric problems or high-dimensional problems. So the normal means model is the model in which you observe a single, you observe observation I, yi from 1 to n. The mean here for yi is theta star I, and there's this additive noise, which is basically sigma times standard normal. So if I want to write this as in vector form, basically we have yi up to yn. This is going to be vector y. This is theta star 1 up to theta star. And this is going to be theta star. And then we have w1 up to wn. That would be vector w. So it's a very simple model. So what is the significance of this model? The significance relative to maybe classical Gaussian location family is that the theta stars are allowed to vary per observation. Okay, and so if we don't put any assumptions on this model, it's really not much that we can say about estimating theta star, because for every I, basically for theta star I, you just get to observe one sample. You could say more, let's say if you change your loss, so your loss is not, let's say your loss doesn't care about individual values of theta star, but let's say aggregate value like an L2 norm distance, then this problem should look familiar from 200B. Anyone remembers what are some surprising results about this model that we saw where you worked out in your homework problems in 200B? Even without any assumptions on theta star, there are some things that one can say if, let's say, you look at the quadratic loss. Anyone remembers? So if you go back to your homework problems, there's this James Stein phenomena that if you look at the maximum likelihood estimator, you can uniformly beat it in quadratic, in terms of the quadratic risk, using a different estimator, which shrinks towards 0. So if dimension is bigger than, so this has to be n actually, sorry. If dimension is bigger than, if in this case, for example, n bigger than or equal to 3, James Stein phenomena so I encourage you to go back and look at this for quadratic loss. But the problem is not that, to be honest, interesting without extra constraints. So what will help is that you're going to assume that theta star, let's say, is in some theta. And this theta is some structured subset of Rn. Then many problems can be reduced to this kind of setup. So why, how can we reduce non-parametric regression to the setup? So anyone can see how non-parametric regression, so non-parametric regression is like yi is equal to f star xi plus let's say sigma wi. So the parallel with what is the parallel with non-parametric regression? So wi IID normal 0, 1. And I think the parallel is quite clear, so people don't mention it. So maybe let me. So let's define a map that maps f to this vector. So any function that you give me maps it to 1 over root n f of x1 up to f of xn. Okay, so phi is a map from, let's say, the function class to, what I say, the set of functions. I'm going to write it as like this, or sorry. This is the set of functions, real valued functions on x to r n. So set of real valued functions on x. In other words, the set of all f such that f is from x to r. Okay, that's this set. And so any function can be mapped to Rn via this transformation. And you can also verify that this is phi is a linear map. Mapping an infinite dimensional space to n-dimensional space. So using this, I can look at yi divided by root n, let's say. I can always rescale my observations. And so I would get something like this. Then what I would have is, if I collect them into a vector, you can see that this would be phi of f star sigma over root n, and then this would be w. Okay, so we're reduced to, so if I call this data star, this is in Rn, so this is a version of the normal means model. Okay, and I can call these, let's say, call this y tilde I. Okay, then I would have y tilde is equal to, or this is just y tilde 1 to y tilde n. So after normalization by root n, you get back an example of this normal means model, where now, what is theta? What is theta? The parameter space of interest. So it's going to be a subset of Rn, parameter space of interest. So theta would be the image. We can write it as phi of f. Okay, basically it would be phi of f as f varies in f. So the image of the function class under this map would be theta. So the set of all basically vectors of this varies in the function class. So you can imagine for different function class, we would get different theta. So the function classes put restrictions on theta, but then exactly what we're interested in. We're interested in estimating the theta, and there's some assumption on theta. Okay, is this clear so far? So what is the empirical norm of f, that quantity that I mentioned, is squared I from 1 to f squared I, so it's nothing but the tune of the squared. That's exactly this quantity. Okay. And this is, if I call this basically theta, this is just the L2 norm of theta. So what we're doing effectively is estimating theta star, and our performance measure is now the L2 norm. So performance measure on the function space translates to the L2 norm on theta in the normal means model. So the relation, the key relation is this: theta is equal to phi of f is 1 over root n f of xi of xn. Okay, so any measure of complexity of f is gonna translate to, like, if f is a complicated set, it would just translate to some subset of Rd via this map. So theta would be just phi of f. So function class. This is the image of the function class, and this is the, so you can put parentheses here if you want. Parameter space of normal means model. Okay, question, comments, questions? So if this is fine, then we can focus on understanding the normal means model. So in the normal means model, so now let's focus. So let us focus on the normal means model. So the normal means model would be, I'm gonna like forget about the tilde, y is equal to theta star plus, I'm gonna write it as sigma w, and then later for the functional version, we need to change sigma to sigma over root n, as you can see. But let's focus on the normal means model. So what is a good estimator? So theta star is in theta. So what is a good / natural estimator of theta star here? So let's see if you guys can now participate so that I know that you're there. What is a good estimator here?
Is it just yi?
Yi?
I mean, yeah, just theta star I is y, or theta star is y.
So that's a good estimator without any constraints. So like theta hat equal to y. This is the MLE when we put no restriction on theta star. Okay, that's the MLE actually, because well, if you write down the MLE, that would come out, which is an uninteresting estimator. And the thing that I mentioned about the James-Stein here, you can show that in fact without any restrictions there is a better estimator if you care about the quadratic laws, which is what we care about. So James-Stein estimator beats this uniformly for quadratic laws, or risk if you want. So review the homework for 200B if n is bigger than or equal to 3. But there's something wrong with this estimator, because I'm having that extra information, and this is not using that information. So y is not most likely in theta. So what is a better estimator? Anyone?
Sorry.
Sorry, I'm guessing you can project this estimator into the space of theta star, capital theta.
Great, yeah, so that would be like the projection estimator. Projection estimator, similar to the functional version we discussed. So theta hat would be argmin, or one of the minimizers, any minimizer, could be multiple, of y minus theta squared. So this is like the Altoona projection. So you find that the theta in capital theta that's closest to y. And this is also easy to show that this is also the restricted MLE, which is like restricting your parameter to be in theta. That's exactly what you get, which is what you should do if you have this restriction. So they're restricted MLE of theta, or theta star. Okay, so that's the key estimator, and that's what we're going to analyze. And so we're not going to worry about how to compute this. We care about like abstract mathematical or statistical results. In practice, it may or may not be easy to compute this depending on how complicated the set theta is. And it could be really complicated if this is an exotic function class. This could map out a very complicated set. So we're going to have to assume some things about this set. But the statistical analysis is interesting. So it reveals some sort of geometric, it reveals that some sort of geometric properties of this set would affect the performance of the estimator. And this is like a general theme in high dimensional statistics. The complexity or hardness of the problem relates to how this guy looks. And in fact, the geometric sort of like idea is sort of local in a sense, as we'll see. So the performance of the estimator depends on the local geometric properties of theta. So far clear what we're going to do. So you have this simple model, and you have this relatively simple looking estimator, although it might be complicated to let me mention this. We are interested in analyzing the performance of theta hat from a statistical perspective, will not worry about how to compute theta hat. So in particular, if this is non-convex, it might not be possible to obtain this global minimizer. So we'll leave this out of the discussion for now. So is the problem clear? So we have the model and we have the estimator, right? Sort of, okay. I'll see a thumbs up. And it sort of can't get simpler from an abstract perspective than this. So the model is very simple. The estimator is like, simple looking. But it turns out that like complicated, interesting phenomena can be observed in this, even in this simple model. So I'm going to use, I said, a bunch of notations here which are not standard, but I'm going to use them throughout. So for any set in RD, I'm going to write theta of u for the intersection of theta with the ball, L2 ball of radius u, or this guy. So if I have, let's say if you have a set here, sorry, let me do the set like this. So I have a set. Sorry, let's try. I'm going to point out some properties of this. Can I do? Yeah. So let's say I have some set like that. So my theta could be like this. That's my, let's say, theta. I'm going to look at a certain point here. And so what we care about is, in fact, in this centered version. So let's say I have a theta star or theta naught. Say this is theta star, for example. I'm going to shift the set to theta star. So this is like, is going to be our so let's not do this. Okay. So let me try to geometrically picture. So let's say the copy this. I can show this. Okay, suppose I have something like this. That's the set. That's the theta. This is the origin. Okay. First, I'm gonna let's say my theta star is here. What I'm gonna do is I'm interested in this centered version. So theta star. So I care about not around the origin, but first I shifted to theta star, which is just this shifted version. And so we're going to look at this guy. And so I first where should I paste? Sorry. See if I can paste. Paste. Okay. I first shifted to this theta star. Let's say that was the more or less. Let's say this was theta star. Okay, so now theta star is the origin here. So this is theta minus theta star. Okay, and then I'm gonna put a ball of radius u around this. Okay, so let's say ball of radius u. So the radius here is u. So this is going to be this thing here. Right. So this thing is going to be theta star u. Okay, so if you do a ball of radius u intersect with this centered theta, that's that set, and it turns out that the geometry of this set, this local set, as you vary u, this would look different. So if u is very small, so if u is very small, you can see that you're going to just observe like the full ball, the full two-dimensional ball. As you increase u, you might like end up observing this like exotic set, right? So the shape of the set varies as you vary u, and you want to measure how big this set is. And the way we're going to measure it is via this notion of, so you can measure it by, let's say, using the entropy idea, like metric entropy that we discussed. There's an equivalent, or not equivalent, but very closely related concept in chapter 5, which we didn't go into, and that's measuring the size of the set using a Gaussian process. So define this so-called Gaussian complexity or Gaussian width as I have written here. So for any set T in RD, we look at the expected supremum of this quantity where W is a standard Gaussian vector. Okay, so what this is going to do is, yeah, I wish I had a better. Yeah, this is too symmetric. Okay, so let me illustrate what this means. I'm going to do it like this, a little bit differently. And then maybe I'll cut. Yeah, okay, so I'll cut some part of it. That didn't work. Okay, so let's do a different set. So suppose I have something like this. That's my set. So what we care about is going to be like the gamma of this thing. What we care about is, it turns out the gamma of theta star u. That's the quantity that I want to understand. But what this is saying is that for any set T, say this is set T, what this is measuring is that, let's say this is the origin. I'm going to pick a vector, random vector W, which is in this case normal. It means 0 and covariance identity 2. This is a normal vector. And then I'm going to take the inner product with theta, and then I'm going to look at basically maximizing this function. Theta maps to W theta. Okay. So the level sets of this functions are are things like this. These are the level sets. Okay, everyone understands the level sets of. Sorry, let's maximize. Sorry. These are the level sets of the linear one. So the level sets of the linear function would be that, the level sets of, so this is going to be one level set of theta maps to absolute value W theta. Okay, so it's going to be like symmetrically on both sides of the origin. Another level set would be, this is another level set, so symmetrically. So they're going to be perpendicular to this direction. Okay, and so in this direction, this particular direction, if I maximize over theta, what I'm going to do is essentially I'm going to like the on this level set that gets like touches the boundary of this, or gets tangent to this. Sorry, I have to take. So this might be like outside here. I don't know. That not necessarily going to touch it. Yeah, I wish I had a better way of sliding. So this might be here. So I have to make this level set big enough such that the last time I like hit this or intersect with this set, that's the time that I'm going to get maximized over the set if I increase it more than this. So this is max W theta in T. This is the last time I'm going to intersect with this, and so the level of this set is going to be basically that's going to be the distance here, sort of from the origin. So what this is doing is measuring the width of this set. You can see in this direction. So you're measuring the width of this in this direction, and then I'm going to change the direction. If I change the direction to something else, sorry. If I change the direction to something else, I'm gonna have like a different like tangent setup. So I'm gonna measure the width in that direction as well. Then I'm gonna have to like measure this in that direction. That's the width of the set in that direction, and then I'm gonna vary this. And in every direction, that's another W. So randomly I pick this and I sort of measure this width in these random directions, and so this is the average. This is going to be the average width of the set. And in high dimensions, this should be again n. When n is large, you know that n large, W, the norm, is going to be very close to root n. So these are going to be on a sphere of radius root n, and the only thing that matters is the direction. So it's like we could have like replaced this with W divided by the norm of W. This would be uniform in the sphere, and this is also some other quantity that people consider. But with the Gaussian, it's simpler because you don't divide by that norm, and it effectively behaves like a constant norm vector. So W in high dimensions is effectively a direction. And so you're going to measure this direction, the width of the set in these random directions, and the Gaussian complexity or the Gaussian width would be the average width. So it could be like in a very particular case. So a set that has, yeah, let me mention it here. So a set that's like very tiny in every direction, but there's like a very sharp, like very spread out in a single direction. Worst case width of this is very large. So Gaussian width would be small. Will be small because you're taking the average. Almost all the directions, actually, like almost all the directions miss this like tiny, like spread, and then for the majority of the directions, you're gonna get these sections. Okay, you're gonna measure it like this. Very unlikely that you're gonna end up having a direction that measures it like that. That's let's say it's just one direction. It's like probability is 0. So the Gaussian width would be small for such a set. Does that make sense? So this is an important concept. Anyone has any questions here? You see why this is like a measure of how big a set is? Okay. One thumbs up. Any other like concerns, questions? So the setup is this. So we're gonna look at it like there's a true parameter theta star. And then there is this set theta. We're gonna shift it to theta star. So we're gonna center it like that. And then I'm gonna look at a ball of radius u around this and the intersection with this set. So that's this guy here basically. And then I'm gonna look at the Gaussian width of this as I vary u, and this sort of measures the complexity of that set locally around theta star. And it turns out that that complexity sort of determines how fast this estimator converges to theta. So this is the theorem that we can prove. Suppose that y is generated from the normal means model that we discussed, and theta star is in theta in subset of RD. And I'm going to assume that theta star is star shaped. I'm going to get back to this. So theta star is star shaped. Sorry, theta of theta star. This is like the centered guy here is a star shaped. And then the projection estimator is what we have considered here and before. Then we have this bound for any u and for any t with probability, high probability. Let's say you have this, and this quantity, there's the noise variance, which appears in the normal means model. And this quantity is, you can see, is mainly determined by the Gaussian width of this set, plus this part, which accounts for the high probability bound. Okay, so that's the main result. And then a lot of consequences follow from this. This result is not stated in your book like that, but some of the consequences are stated. So the only assumption that we are making here is that theta star is star shaped. So I'm gonna shift everything to the origin, and then I'm gonna assume that this is star shaped. What is star shaped? Anyone knows what this means?
That if you multiply like a point in your set by t between 0 and 1, it's still in the set.
Okay, yeah, so let's do it with alpha, let's say. So theta star is star shaped if you pick like, let's say, what should we do here? I don't want to say theta. Let's say v in theta star, and alpha in 0 to 1. Then alpha v is in theta star. So something which is star shaped is something like this would be typical example. For example, that would be a star shaped. Say this guy. The reason being is if I take, forget, it's just inside of this. Can't do a good job. Something like that. If I take any point here, anything between 0 to that point is inside the set. So basically, the intersection with any ray from the origin is sort of convex, if I'm not wrong. So the entire, if you look at the ray, like the entire, this would look like a line segment. Something which is not a star shape is, say, something like that is not star shape. Okay, so if I take something here and if I join something, some part of this is outside. So this is a mild condition, fairly mild condition. It's much more relaxed than convexity. So if things were convex, then this would happen, but this is much milder. And so the reason why we also like say so a star shape could be like generally with respect to the origin. But I could have said that the original theta is star shape with respect to theta star, which is basically shift everything to theta star, and then with respect to the origin, it's star shape. So this is clear to people now. That's the only condition that we're going to use, or maybe you're going to use to prove this. Just sketch the proof. So is the statement clear? So how do we use this result? So this holds for any u, and we have an upper bound. So the natural thing to do is to consider, you want to maybe, when you have a bound, you want to maybe find you have a parameter here, u, and you want to make this small as possible. In order to make this as small as possible, you can sort of argue for yourself that to make the bound as small, to make the bound as small as possible, like choice of u. We should roughly set the two terms equal, as small as possible. We should set the two terms equal. Okay, so I should, or up to constants, you could say, but it's natural to try to set these to be the same. And then if I do this, what I would get is root 2 sigma, one of them cancels out, okay, divided by u is equal to 1, or 2 sigma g u, and t u squared is equal to 1, or let's see, how do I write this? Yeah, you could say just 2 sigma g u t is equal to u star. Okay, or equivalently, if you remember what this is, it's like gamma, that's the g. Right. Sorry. Move it here. And I'm going to write this as GUT is u squared divided by 2 sigma. And then this is equal to gamma theta star u plus tu is equal to u star over 2 sigma. Right? Okay. And then the next step is, still seems complicated. What you want to do is, now I both have a t and u. So to get a balanced bound, it's natural to assume that every piece of these two terms is like up to constant equal to the other side. So if this is much larger than this, or this is much larger than this, then we're sort of losing. So we want these two to also be roughly the same. So I would say basically I want gamma theta star u to be of the order. This is like up to constants of the order of the other side, and also tu up to constants to be of the order of the other side. But if you think a little bit about this, this suggests, for example, that u has to be roughly, or t has to be, I have to take t to be roughly u over sigma. And this gives me an equation that I can solve for u, and that gives me the right choice of u. And that would depend exactly on the complexity, this complexity of this set. So if you want to make it precise, we can make it more regress by saying, or by defining, by letting, let's say, or say, assume that you satisfy, or this is the smallest, or that's okay. We don't need to like say smallest. Assume that u satisfies gamma theta star u less than or equal to, let's say, kappa u squared over 2 sigma, for example. If that's the case, then yeah, something like that, then I could have a corollary. You can easily show that the result would simplify to this. I'll let you show it. And then if I take, for example, t to be u over sigma, like the one that we had here, then you can see the two terms are also going to be the same, of the same order, would be of the same order, and the whole thing would be, as a kappa is a constant, this would be of the order u. Okay, so any u that satisfies this would be an upper bound on this. So any u that satisfies this so-called critical inequality would be on upper bound on the deviation, assuming that we choose the t correctly. Okay, so then it makes sense to then it makes sense to look at the smallest u satisfying that equation, and you can argue that it's sort of the smallest would be at a point where these two quantities are equal or roughly equal. So if you start from u very large, this is going to be bigger than this. For the star-shaped sets, your book also had like a result that this is going to grow slower than u squared. So this is going to grow slower than u squared. So when you so this is like this, and this is something like that. So that's like u squared, like kappa u squared over 2 sigma, and this is like gamma theta star u, if I'm not wrong. So for a large u, this is bigger, and then there's a point where this is the smallest like u for which this is still bigger than that, and that's sort of, you can see is roughly when you set them equal, not roughly, but exactly. So in practice, what you do is we don't care about the constants. So what we're going to do is like we're going to set this equal to u squared divided by sigma up to constants, and then this inequality allows us to solve for u, solve for the critical radius. And that critical radius would be exactly a rate on how fast the estimator sort of approaches theta star. Okay, does that make sense to people? Questions? So I'm gonna maybe come back to the proof of this later, but I just want to show you how interesting this result is in terms of the kind of things that you can do. So right, there is a, sorry, let's see if I have.
Professor?
Yeah.
So when you optimize over U, the bound you can get will only depend on sigma, right?
Here?
Yeah.
You mean something like that?
Yeah.
It's also going to depend on the dimension, sort of. Let's see if we can, how can I make this? I'm going to show you examples of what this would look like. Let's see if I have the right. Okay, see if I have the right choice here. So this kappa, actually, what we're going to do is, I'm not going to, so let's take kappa to be, let's say some sort of a c root n. You'll see why this would make sense. Then or should we do this? I'm not sure. Things are a little bit. Stop here. So let me try to see if I can. Usha, I'm going to show you an example. See how things go. We'll figure this out. So we might need to take kappa to be something more interesting related to the dimension, but it doesn't matter. Even if you don't do it, you should get the right result. So let's try to give an example. Well, let me just mention another corollary which you can prove. Maybe I'll assign it as a homework problem. Corollary 2 is that because you have this bound, if you take the expectation, you can show that the expectation of theta hat. So that would get rid of the theta automatically. You don't need to worry about theta. This would be up to constants bounded by kappa squared, u squared plus sigma squared. So that's the kind of bound that you get. And the idea is like, the hint is like use the fact that expectation of y for a positive variable is like probability of y bigger than t. Y bigger than or equal to 0. So if you integrate this, you'd have this bound. This is easier to work with instead of working with the high probability bound. So both hold. So let's try an example to see how this works. Example. So what I would like to do is, so consider, we're going to do like sparse regression, but with the L0 node, sparse regression. And you can view it as an instance of this, but the prediction problem, not the recovery. Recovery of the beta. I mentioned there are 3 versions of the regression problem. One is recovering the parameters, which we did, like the L2 distance. The other is the prediction problem, which is actually figuring out the value of a star. So the problem that we're doing here is like very similar to the prediction problem in regression, like the linear regression. And then the third is model selection, which we're gonna skip. So we're gonna look at this version. So suppose X is in R n by P. I forgot whether we use D or P, but P is the dimension. Let's say that's the design matrix. And then we have, I'm gonna take theta to be the set of all X beta, such that beta is in RP. And so if you look at the regression problem, Y is X beta plus epsilon, right? And then epsilon is normal means 0, sigma squared I n. So this is, we're calling this theta. So if you call this theta, that would be exactly the normal means model. So you can think of the linear regression as a normal means model where you have the assumption is that theta, usual linear regression. This would be theta. This is like the image of X in like functional analysis. This is written as image. So you're restricting theta to be in the image of an operator. This is usual regression. So sparse regression. So let's say this is theta tilde. Sparse regression, which is theta of our choice here, this is going to be X beta such that beta is in RP, and beta, let's say, is the L0 is bounded by S. So it's S is sparse. So I can think of this as the image of the ball of radius S, L0 ball in RP under the map X. So I'm looking at the image of that ball. And so this would be a union of subspaces. So if you think of so B0 of 2 and 1, this is going to be just that, just the L0 ball of radius 1, it's like 1 coordinate non-zero, in R2 is the union of these two. And then this guy would be, so this would be like n by 2 in this case, if P is 2. Then this would be like, you'd have 2 vectors in R. This would be like R n. So you'd have 2 vectors. These are the columns of, so X, let's say star 1, this is the first column, this X star 2. And then what this is saying is the union of these, it would be the union of these 2 subspaces. Okay, so that would be the theta. So in Rn, this would be a union of subspaces, spaces spanned by the columns of X. Okay, and then if I look at, so we have, if I look at theta of theta star, so this would be like a beta star, this would be theta star, that would be theta minus theta star. And then this would be like X B0 P of S minus beta star. Okay, so it's like shifting this to beta star, which is like shift everything here to, let's say beta star itself is beta star, it belongs to B0 of S as well. So the true vector is in B0 of S. That's what we know. So it's like here, I'm going to move the entire thing here. And then it would be like going to something here. So this would like move to that place. You can see this is not going to be star-shaped relative to the origin necessarily, but this is going to be inside X. You can easily argue that this is, because this is S sparse here, everything is S sparse, this is going to be inside this guy. Okay, X, image of X, image of a ball of radius 2s, L0 ball of radius 2s. And this guy is S sparse. This is star-shaped. And when we go over the proof of this result, you can show that you can replace this with any superset. And that superset appears here. And if that superset is star-shaped, then everything goes through. So you don't need to worry about necessarily this, but any set that contains this and a star shape can be replaced. You can replace it with that. So we're going to replace this, apply the result to this instead of this. This is not star shape, but is inside that star shaped set. And so the estimator, sorry, you're a little bit going over. I'm trying to be fast here. The projection estimator is this, is equivalent to, so when you're trying to project onto this, you're effectively projecting onto, so that's the general theta is the general theta in that set. Theta varies in that set if like theta is like X beta where beta is in the ball. So this is the estimator would be, theta hat would be just X beta hat, and is obtained by solving the L0 constraint progression. And so what we have is, so if I call this, I think I have some notes, I call this set U. Instead of working with this, we're going to work with U. So the key is the Gaussian complexity of U intersect with, so you have to intersect this with a ball of radius. I'm going to do it with radius instead of U delta. And that's just this quantity. This is theta, this is like theta star intersect with this. And then the critical idea, like the radius would be computing this, compare this with U squared over sigma. Okay, so we have to figure this out. And we're out of time. So I'm gonna maybe post the slides or try to give you hints, and maybe for the next time you can try to argue this for yourself. This is not easy, but I'm going to assign it as an exercise. You can think a little bit about this, but we're going to come back. This is doable, so you can compute the Gaussian bit of this. You have to intersect it with basically something like that. So you have to intersect it with a ball of radius U, and then determine the complexity of this intersection, the Gaussian complexity of this intersection. And they just mentioned this, and then we're done. So this is going to be delta root S log P over S, something like that. This is going to be of this order. And then you can solve this equation, and then you get a rate. Yeah. And then N is missing here, so there should be some N somewhere. I'm going to fix this hopefully, and then we'll come back, and then you see that the role of the N here, which is missing. Okay, sounds good. We can chat like in the office hours. Sorry that we went over a little bit. So I'm going to stop here, come back next time, and try to finish this exam. Okay.